Before we actually move into any new material, let me just ask if there are any questions on anything. If you managed to get started with integration by parts, any concerns or questions about using that table method of integrating? Any questions from anyone? Okay. Not seeing any questions. Again, I'd like to encourage you to either unmute yourself and ask. It's faster than typing. Of course, you're always welcome to type questions in the chat as we move along. So again, today we're going to be talking about more integration methods. And you might remember we've discussed indefinite integrals that give you a function, an antiderivative function, kind of a total function when you integrate a rate function. We've also talked about definite integrals that give you a number. Okay, it's important again to keep those two straight. You're essentially doing the same process. The only difference with definite integrals is you're actually evaluating your antiderivative at the upper bound of the definite integral minus the value at the lower bound. This has an analog to area between your function curve and the x-axis, with the caveat that area is negative if it's underneath the x-axis. Okay, so that's just a quick summary of kind of the meaning of integration. What we're going to be talking about today has an unfortunate name. They're called improper integrals. And there's nothing improper about them any more than there's anything improper about improper fractions. Okay, it's just a name that kind of stuck. And what improper integrals are integrals that have one or more of their bounds at infinity. So you can think of this as if you have an applied problem and time is your variable, it's like what happens to this function into the indefinite future. Okay, you could think of this as, I think I mentioned a few examples like rent on an apartment complex that goes into the indefinite future, compounding into the indefinite future on investments. Things like mines or oil wells, if you're interested in the total income from that type of an investment. Those are all things where you might use an indefinite integral to calculate the total value. And next week, we'll see some applications of integration, not only in physics or basic stuff, but also in business. Okay, so you can see just what these things could be used for. Okay, so today we're going to kind of focus on the mechanics of finding the value of an integral when its bound is infinite. You might recall from early on in the class, one way to do this is to take a limit, okay, and let the limit approach infinity. When we get into the discussion, we'll also talk about integrals that aren't defined at one or the other of the bounds, and we can evaluate those in the same way by taking a limit as you approach the value of that bound. Remember that the value at a particular x is not the same thing as the limit as you approach x. It doesn't have to be. It can be, but it doesn't have to be. So we're going to kind of have to review a little bit of limit stuff in order to be able to handle the material in this section. Okay, I'm going to begin by sharing my browser and show you where we are in the course. Okay, we're currently in week 13. Okay, and here's the integration by parts stuff. Here's the improper integrals material. And I'm going to be using improper integrals notes. Okay, so if you want to open that file, or if you already printed it off, great, whatever. Okay, but I'm going to be looking through that as we move through the class. And again, if you have questions on anything as we go, please feel free either unmute yourself and ask your question or pop it into the chat. Okay. And again, let me share the content with you. All right, so now everybody should be seeing 3.5b improper integrals notes. And again, these are excerpted, but they're not exactly from the online textbook that's included in your course. Okay, I kind of excerpted the highlights. Okay, so to start out, remember definite integrals give a value, and our ability to find the value, okay, of a definite integral was dependent on assumptions, okay? Namely, that we had a finite length of an interval between A and B, okay? So in other words, no infinite bounds. And the other assumption we made was the integral was defined at every point in that interval, including the bounds, okay? So the function was defined and bounded. So in other words, there are going to be situations where if you were to try to take a definite integral, you won't actually be able to get a number. We kind of implied, okay, with some of the questions that were in the practice exam, the last practice exam and the exam itself, if you had a definite integral, okay, and it became undefined at some point within your bounds, okay, you couldn't use the fundamental theorem. Okay, remember that one? We had an integral that shot off to infinity in the middle of the interval of integration, and we said, yeah, we can't do that. Okay, now it turns out if your interval is undefined at one of the endpoints, we can try taking a limit there. Okay, so that's a slightly different situation. Okay, so we're going to be looking at two cases of improper integrals where one or both of the bounds are infinite, or where the integral isn't, the function you're integrating isn't defined at one or the other of the bounds. Okay. Okay, so sometimes, again, applied problems require us to handle these assumptions not being true. Okay, and here's one of my other examples. Say we want to find the total amount of pollutant a company dumps into a river in the indefinite future. Let's assume they wind up having the EPA get on their case and basically tell them, hey, you're not allowed to dump this pollutant in this river. What are you doing? And basically they say, all right, we're going to tail it off. Give us a break. We'll tail it off over the indefinite future and we'll pay a fine. Okay, and the fine they pay is going to be connected to how much they dump, right? So it's in their interest to know what that number is. Okay, that's an example of, using an indefinite integral. Okay, sometimes they're called improper integrals. Again, that's an unfortunate terminology. It's just a type of integral. So how do we handle these? Okay, so one thing we can do is we can call our infinite bound. It says shrink it. You're not really shrinking it. You're basically saying, all right, pick some number to be the either negative infinity bound or the positive infinity bound. Like let's call it A or B or whatever. And then we're just going to let it get larger. Okay, we're going to let it approach a limit. Okay, so again, the value of the improper integral is whatever that limit is, if it exists. Okay, and it's possible that the limit won't exist. Okay, so again, this is kind of not a case we've talked about yet. Okay, whenever you've done a definite integral, except for one that was undefined in the middle somewhere, okay, you got a number. Okay, but it's possible that you'll take a limit at one or the other of these infinite bounds and you won't get a valid value. You'll get infinity or you get does not exist. Okay, then the integral is said to be divergent. Okay, so that integral is said to be divergent. That means it doesn't approach a value. okay? Or you say the integral diverges, okay? Otherwise, it's convergent. It's going to approach a particular value, okay? So you can think of divergent as going like this, convergent coming into a value, okay? All right, so we will have to take limits to do these. So again, we'll kind of review a little bit about limits, okay? So let me do a little limit review over here. And again, this is hitting the high points, okay? If you take a limit as x approaches infinity of 1 over x to the n, okay? Basically, what I have here is I have a fraction, okay? And this can be either x to the first, it can be x squared, it can be x cubed, right? But some power of this value, but it's in the denominator, okay? And again, what you want to realize, if the denominator of a fraction gets large, this limit equals 0. Okay, so as the denominator gets large, the fraction approaches 0. All right, and again, you can think about this by just plugging in some numbers for x, right? If x is 10, you have 1 over 10, that's 1/10. If x is 100, you have 1 over 100, that's a lot smaller than a tenth. If you plug in 1,000 for x, you've got 1 over 1,000, that's even smaller than 1/100th. You can see the value of the fraction is getting closer and closer to 0. So if you push x all the way out as far as you want, you're approaching 0 with the value of the fraction. Okay, here's another limit thing that you might or might not remember. If I have e to the x, and I take the limit as x gets huge, okay, that limit does not exist. That basically becomes infinite, okay? But if you do one of these two things, you either let x approach negative infinity and keep it as e to the x, or you say x approaches positive infinity and you have e to the minus x. These approach 0. Okay, for the same reason. Remember what 1 over e to the x is. Okay, e to the x is blowing up, but this says it's in the denominator. Okay, likewise, if you let this approach negative infinity, you're doing the same thing. Okay, so these are two limit examples you need to remember. Okay, you need to remember these examples. So let me ask questions on either of the limit review examples before we get started. Okay, please ask. Again, I'm pulling information from way back in the course. Anybody have questions on either of these examples? Okay, in my experience, the one with the e to the x is confusing to a lot of people. Okay, so please, make a note of it. If you've got negative stuff going on in the exponent, your e value is going to approach 0. Okay, regardless of how it gets there. Okay, with a limit. All righty then. So if any of these limits do exist, we're assuming for this discussion these limits exist. Here we have a definite integral of f of x dx, where f of x is some kind of a rate function. And here my upper bound is infinite. Okay, so what I'm going to do is I'm going to call my upper bound C. You could call it K. You could call it Harry. It doesn't matter. Okay, and then you let whatever variable you picked for the upper bound approach infinity with a limit. Okay, so you do your antiderivative the way you normally do it. Okay, and then this kicks in when you try to use the fundamental theorem. Okay, then you actually have to take a limit. Okay, so you do a regular antiderivative. Okay, and this is important when you do the fundamental theorem. Right, where you subtract the upper bound minus the lower bound. Okay, so basically, I want everybody to understand we're not doing anything different with the integration. Okay, it's the evaluating at the bounds is where the limit stuff comes in. Likewise, suppose your lower bound is negative infinity, then you just put your constant of choice as your lower bound and take the limit as that value, that constant approach, that variable approaches negative infinity. You're just going to push it way out. Okay. So again, evaluate the proper integral, or I should say, do the antiderivative first. Okay. And then take the limit when you're using the fundamental theorem afterwards. Okay. And here are the terms I introduced, okay, before. Okay, except I can't spell. All right, so basically convergent means you can get a value for the definite integral, and divergent means you either wound up with an infinite limit or the limit doesn't exist. In any event, you cannot get a value for the definite integral. That's called divergent. Okay, so any questions about the stuff in the box? Questions about the definitions in the box? We good? All right, so we're just showing how we're going to do this. All right, and I realize that somebody talking at you how they're going to do it isn't anywhere near as valuable as seeing how they're going to do it. Okay, what you want to take away from the box is we're going to plug in a variable for the infinite limit and then do the anti-differentiation, and then we're going to take a limit at the end. Okay, so let's see some examples. Okay, so here we have an infinite upper bound on the integral. So according to our strategy, we're going to rewrite it like this. Okay, we're going to put a C in for the infinite bound. And then outside the integral sign, we're going to let C approach infinity, because again, it was our upper bound. Okay, so first we evaluate the proper integral, okay, which involves us taking an antiderivative. Okay, so again, we have okay, I'm going to rewrite 1 over x squared as x to the negative 2 dx. And again, I'm going to do that because I want to be able to use the power rule for integrating. Okay, so I just copied my integration problem over again, and I just rewrote 1 over x squared as x to the minus 2. Okay, now I'm going to use the power rule on this. Okay, so this basically says add 1 to the exponent and put that over the new exponent. Okay, I still have the limit as C approaches infinity. And now this gets evaluated from 1 to C. All right, let's do a little cleanup. Okay, and I get the limit as C approaches infinity. Do not lose the limit statement. Okay, and I have negative 2 plus 1 is negative 1. Okay, so I have x to the negative 1 over negative 1. All right, and again, all of this is just algebra. Okay, so keep my limit statement. And x to the negative 1 is 1 over x. And I can put the negative sign in the denominator out at the front of it. Okay, so that's all a bunch of algebra. Anybody questions about the algebra? And again, I'm careful not to lose the limit statement. All right, now here is where this limit statement comes in. Okay, I have the fundamental theorem. And I have the limit as c approaches infinity of -1 over c. Okay, that's the first part. Minus. Okay, and now I have the second part. Okay, which is -1 over 1. Okay, so here's my upper bound, and here's my lower bound. Right, this is the fundamental theorem bit. Okay, so notice again, I got a perfectly fine antiderivative without doing any limit stuff, except carrying it along. And now when I'm doing the fundamental theorem part, because it's a definite integral, here's where I have to take the limit at the upper bound. Okay, now take a look, okay, at this part. As c gets very large, what happens to -1 over c? Okay, I'm asking you a question over here. What happens to -1 over c as c gets very large? Okay, you can put your answer in the chat, unmute. What do you think I should put here? Does this limit exist? Okay, well, the denominator gets large. Okay, the denominator c gets large, which means the fraction approaches 0. Okay, the denominator is what's getting large. Okay, so that means, again, if the denominator of a fraction blows up, this becomes 0. It's approaching 0 from the negative side, but it's still going to 0. Okay, so the value of this limit is 0. Okay, and I got rid of the limit statement because, again, I took the limit. And then I have minus a -1 over 1, and that's just plus 1. Okay, so the value of this integral is 1. Okay, so this is a definite integral. Okay, and the value approaches 1. Okay, out into the indefinite future. Now, just so you can see what I'm talking about, okay, let me show you kind of how you can fake this out a bit. Okay, so I'm hoping this works with Desmos. If not, I'll have to use a TI, but I know everyone has Desmos. Let's see what this means in Desmos. Okay, so let's see what this means in Desmos. So here's my function, 1 over x squared. And I'm going to go over here to Desmos. I'm going to say y equals 1 over x squared. Okay, so here's what the graph looks like. And I'm interested in it from 1 on out. Okay, so basically what I'm saying is from this line where x is 1, which is right here, all the way on out here, all the way out as far as you want to go. The area between the curve, okay, and the x-axis gradually converges to 1. Okay, now I know there is a Desmos definite integral calculator on here. So again, I'm going to try to see if I can find that. Okay. All right, and they give you kind of a built-in function. Okay, and suppose I don't want to use their function. Suppose I want to use mine. Okay, and again, I'm starting with a equals 1. They only let me go out to 10. Okay, but if I take a look, you can see the value's already at 0.9. If they let me go out further here, like say they let me go out to 100, and I stepped in ones, okay, I'm just changing this so I can see it. Okay, and I push this all the way out. Look at what's happening to my value of the area. It's at 0.99. Okay, and you can see the shaded area. Okay, so you can see this value as x gets larger is approaching 1. I can even change this limit and make it 1,000, and I'll step it in 10 because I don't want to break Desmos. Okay, push it all the way out. Now I've got 3 nines. Okay, so see how the area is approaching 1. Okay, so again, this is a graphical representation of what's happening. Okay, you can also do this on a TI-84 since it has a built-in integration, definite integration function in the calc menu. Okay, but again, I just want to make sure, is this idea clear? Okay, is the concept clear? All right, please give me a yes or a no. Does this make sense? Okay, I wanted to show you what 1 means. Okay, so are we good with this? Concept clear? Okay. All righty. Okay. Well, let's take a look at some more examples. Okay, so here I have the integral from 10 to positive infinity of 1 over x cubed. Okay, so I can rewrite that since there's an upper bound that's infinite. I'm going to let c approach positive infinity and rewrite it from 10 to c. Okay, and then I'm going to rewrite x 1 over x cubed as x to the minus 3 dx. Okay, everybody okay with the rewrite? Anybody questions on why I rewrote it the way I did? All right, so now I'm going to evaluate the proper integral. Okay, and that means just do the antiderivative. Okay, so basically that's going to say use the power rule. I'm going to add 1 to the exponent and write that over the new exponent. I have to remember to not lose my limit statement. And now this is evaluated from 10 to c. Okay, cleaning up the numbers a little. Okay, this is -3 plus 1 is -2. And a -2 down here. All right, and taking it one step further, okay, this would be a 2 in the denominator, okay? I can put the negative sign out in front, okay, and then the x squared will also wind up in the denominator, okay? So using, again, properties of exponents, the whole fraction's negative from the -2 in the denominator, but the 2 still is down there, okay? And I can rewrite this as x squared in the denominator with a 1 up here. Okay, everybody all right with the algebra? Okay, again, -2 in the exponent flips the x squared below the fraction bar, leaving a 1 up here. Okay, and the negative sign just came out in front. All right, so now I'm going to use the fundamental theorem. Okay, and I'm going to start by evaluating it at the upper bound. That's the limit as c approaches infinity of -1 over 2c squared. Right, that's my upper bound. And then I'm going to evaluate it at the lower bound, which is -1, that's a 10. Okay, 1 over 2 times 10 squared. All right, and there's my lower bound. Yes, thank you, Nee. I just caught that. 10 is the lower number. Okay, so I plugged in 10 for my x. Okay, so here's the same antiderivative expression evaluated at c, and here it is evaluated at 10, right? Now, if I let c approach infinity, okay, notice the c is in the denominator. So my question is, what happens to 1 over, I guess I should say negative 1 over 2c squared as c gets large? Okay, what happens to this? Anybody have a thought? Okay, anybody willing to answer what happens to this fraction as c gets large? Okay. Again, think about this. You've got c in the denominator and it's getting very large. You're also squaring it, which means it gets larger faster. Okay. So the denominator is getting huge. So the fraction is approaching 0. Okay, this fraction right here. Okay, I'm looking at the first fraction at the upper bound. Okay. Basically, c is getting large, so large, it overshadows everything else in that denominator. Okay, it doesn't matter that you're squaring it. It just means it's getting larger even faster than if you left it alone. Okay. And if you multiply it by 2, it doesn't matter. If c is something like 10 million, all right, so we doubled it. Now it's 20 million. It's still enormous, right? So this whole fraction approaches 0. Okay, then over here, we have, what do we have? We have a 1, negative 1 over 2 times 10 squared. 10 squared is 100, and 2 times that is 200. Okay, and then notice we have 0 minus a negative number, which means we have a positive 1 over 200 for our value. Okay, so questions on the first 2 examples? Questions on the first 2 examples? Anybody? Okay. Not seeing any. Okay, so I had a question in the chat. Whatever the lower number is, the fraction will be 0 as long as this denominator is approaching infinity. Okay, so basically I have something that's growing enormous, huge. Then I square it, so it's like 2 times itself huge. Okay, and then I double it, so double 2 times itself huge. It's still enormous. The denominator's approaching infinity. So the fraction approaches 0, yes. Okay, and that's important to pay attention to. Okay, any other questions? Again, I find this is not intuitive to folks. So again, please ask if you've got questions. Okay, well, we had some really simple examples here. Okay, examples where, you know, we just use the power rule to integrate, but you can use any of your integration techniques. Okay, here's an example where, again, we might want to use something other than just the simple power rule. I'm going to rewrite this. Okay, you can see my upper bound is infinite, so I'm going to let C approach positive infinity. This is 3 to C. And again, I'm going to rewrite my integral as x minus 2 to the negative 3 dx. Okay, again, I took the quantity that's in the denominator and I just wrote it with a negative exponent. Okay, so let's take a look at this. Okay, what method of integration should I use on this? Okay, I'm asking you an opinion question. What method of integration should I use? Anybody have thoughts? Hopefully everybody realizes I can't use a simple formula like power rule. I need to use another method. Okay? So let me put something else, substitution or by parts. What method should I use? Okay, does anybody remember how to decide what method to use? I'll wait a bit while you think about it. Okay, we have one vote for substitution. Anybody else want to vote? Okay, this is what I meant last time when I said you won't always be able to tell based on the section that it's in. Okay, I have another one for by parts. Remember, you need to have a reason. Okay, you need to have a reason. Okay, how about if I write it like this? 1 times x minus 2 to the negative 3 is the integrand a product. Okay, the way I wrote it, it is, yes, are the two factor functions related to each other? Okay, here's the question I really want the answer to. Are the two factor functions related to each other? Or are they totally different families? Okay, Nitsan saying yes. Okay, so how are they related? Okay, feel free, Nitsan, if you want to unmute yourself. How are they related? Yeah, okay. One is the derivative of x. Okay, yes, absolutely. So since I'm seeing a product of functions and one function is part or the derivative of the other function, okay, I'm going to use substitution. Okay, notice I had to put the 1 in there to make it obvious to myself. Otherwise, you're looking at it saying, I don't see a product. Remember, you can multiply anything by 1. Okay, and again, the point is 1 has the right power of x to be a derivative of x to the first. Remember, 1 can also be thought of as x to the 0. Okay, so once you see that the functions are related like that, you think substitution. Okay, you're going to use by parts when the functions are not related. Okay, by parts. Everybody good with that? Okay, all right, so let's, again, sorry about the tablet zooming in and out. Okay, so let's see what I can do. I'm going to say let u equal x minus 2. I'll start out with that. And then I have du over dx is equaling 1. Okay, and remember what I want to do is I want to match the other stuff in the integral. Okay, so I want this to be 1 dx. So I'm just going to multiply both sides by dx. And then I get du equals 1 dx, and I'm good. All right. I've already decided that u is this thing. Okay, so now all I have to do is do substitution. All right. And again, I have to keep my limit as c approaches infinity. Okay, and I'm going to put my stuff in here. Okay, and again, remember, I'm keeping the bounds in because I'm going to just do my anti-differentiation. Okay, I'm going to do the antiderivative with my u bounds. Okay, so it might even be better to say, all right, just do the antiderivative with the u bounds and then plug the x bounds back in. Okay, so this would be u to the minus 3 du, where here's the u going in, and here's the rest of it. Okay, I'm going to add 1, okay, to the exponent. That'll give me u to the minus 2 over negative 2, okay, which is going to give me, if I put my my x things back in, that gives me x to the minus 2 to the negative 2 over negative 2. And now I can put my x bounds back in as c approaches infinity. Okay, my lower bound was c, my upper bound is 3. Okay, so here's the u substitution. I did the integration with the power rule, and then I just plugged my x back in, okay, for my u, because again, my bounds on this integral have to do with x, not u. Okay? All right. I can simplify this a little more if you want. I can say the limit as c approaches infinity. Again, I can bring the negative sign out front. The 2 is down the bottom with x minus 2 squared, and there's a 1 up here. Okay, so that's exactly like the last one, except I have a quantity in parentheses, not just an x. All right, so now I'm going to use my fundamental theorem. At my upper bound, I'm taking the limit as x approaches infinity, as c approaches infinity rather, of 1 over 2c minus 2 squared. Okay, I'm just plugging in. So here's upper. And then at the lower bound, I'm plugging in a 3. Right? Now here's a great example of what we were talking about in the last problem. Okay, C is blowing up. It's getting huge. Will it matter if I subtract 2 from it? Okay, will subtracting 2 from C matter if C is enormous? What do you think? I'm asking your opinion. Okay, suppose C is something like 5 trillion. Okay, it's heading on out towards positive infinity. Will subtracting 2 from 5 trillion change it really? No. Okay, no. Not if C is huge. Okay? All right, so then the quantity in parentheses is something enormous. Guess what? We're going to square it. We're going to make it even bigger. And then we're going to double it and make it even larger, right? So this denominator is approaching infinity. I want you to understand no matter what operations you're doing down here, okay, for the most part, you're still going to have a really large denominator, okay? So this first fraction is going to approach 0. Okay, I think you can already see the minus, a minus is a plus. And then down here in the denominator, I have 3 minus 2 is 1, times 2 is 2. So this becomes 1/2. So the value of this integral is 1/2. Okay. Again, please understand, if this had not been in the denominator, if the c had been in the numerator, this part of the integral would blow up to infinity, and we'd have to say the whole integral was divergent. Okay, but because it's in the denominator, when denominators blow up, we wind up with fractions going to 0. Okay, everybody all right with that one? Okay, okay with the infinite endpoints examples. Okay with the infinite endpoints. Okay, I know all of these had positive infinity, but it works the same way with negative infinity. Okay. All righty. Let's take a look then, if you don't have questions, let's take a look at what happens when your integral is not defined at an endpoint. Okay, so now you have to kind of remember what the one-sided limits are. Okay, so here your upper bound is where the integral isn't defined. Okay, that means, again, if you think about the way things work, you've got an interval here, AB. Okay, if you're not defined at your upper bound B, you need to approach it from the left. Okay, so you have to let C approach B from the left. Okay, that's why I have a one-sided limit here. Okay, same idea. I'm going to plug in C for the problematic endpoint. It's just, it's not infinity, it's some value B, and I'm approaching it from the left. Okay, likewise, if you have a problem with your lower bound, okay, here's A and here's B. All right, say the integral isn't defined at the lower bound A, you have to approach that from the right. So you have to basically take the limit as C approaches A from the right. Okay, so basically you're from within your interval, okay, and you have to approach the endpoints from whichever direction makes sense, okay? Upper bounds or upper endpoints you approach from the left, lower endpoints you approach from the right. Okay, everybody all right with the one-sided limits? Everybody okay with the one-sided limits? Again, we talked about those at the beginning, but it's been a while since we looked at that. Okay, and the same rules apply. If the limit exists and it's finite, it's not infinity, okay, or negative infinity, we say the integral converges. Otherwise, we say it's divergent. Okay, so let's take a few examples, right? So let's see how this works. All righty. Now you might look at this, okay? And again, you should pay attention when you have a definite integral and check to see, is this function defined for all of the x's in the interval? Okay, so is the integrand defined for all x in 1 to 10? I'm asking a question. Is the integrand defined for all x's in that interval? Okay, look at it closely. Okay, what happens when x is 10? Anybody tell me what happens to my function here when x is 10? Yeah, the denominator goes to 0. Okay, so basically, the integrand function is undefined when x equals 10. Oops. Okay, when x is 10. Because you have 10 minus 10, that's 0. Square root of 0 is 0. 1 over 0. Can't divide by 0. That's undefined. All right? So the integrand is undefined when x is 0. So we need to rewrite this slightly as the limit. And again, it's my upper bound. Okay, so here's my interval. Okay, I'm interested in what happens as c approaches 10 from the left. Okay, so I'm interested in what's happening there. Okay, everybody see why it's a left-handed limit? Okay, so I'm taking the limit as c approaches 10 from the left, 1 to c. I can rewrite this a little bit to make it easier. 10 minus x to the negative 1/2 dx. Again, I can also use my trick and say, well, it's 1 times that, right? Why am I doing that? Because again, the derivative of negative x is negative 1. Okay, so I'm thinking I'm going to use substitution to integrate. Okay, hopefully you're seeing the pattern. If you have an expression in parentheses raised to a power, an expression in the denominator, okay, which in this case is raised to a power, think substitution, okay? Particularly if you're not seeing another non-algebraic function out here, like an exponential or a log, okay? It's usually pretty obvious when you need to use by parts because you're seeing a log and an algebraic, or an exponential and an algebraic. They're not related. Here I'm saying, well, I just got a 1. Oh, but hey, wait, that's part of the derivative of negative x. Okay, so use substitution to integrate. Right, and I'm going to basically say let u equal 10 minus x. Right, so that matches this. Okay, and now I have du over dx equals negative 1. Okay, then I really actually want to match the dx on a positive 1. Okay, so let me play with that a little. I'm going to multiply both sides by dx. Okay, so I have du equals negative 1 dx. The only thing I need to get rid of is I need to get rid of the negative sign. Okay, so I'm going to divide everything by negative 1. Okay, that gives me negative du equals 1 dx. Okay, and now I match what's in my integral. Okay. See what I'm doing? I have to match it and match the sign as well. Okay. All right, so now let's do the substitution. Again, because I'm doing U substitution, I'm just going to do an antiderivative and then plug in the bounds when I'm finished. Okay, so I don't have any problem with U bounds versus X bounds. Okay, so I wrote it as 1 times 10 minus x to the minus 1/2 dx. Okay, so again, let me look in the rewritten one. I have 1 in dx, that matches. And then the 10 minus x is my u. So I'm going to write this as u to the minus 1/2 times negative du. Okay, so again, here's my u. There's my 1 times dx. Okay, everybody good with that? First thing I'm going to do is pull that negative sign through. That's like pulling a -1 out. Okay, that's like pulling a -1 through the integral. And then I'm just using the power rule to integrate. So that's going to give me u to the minus 1/2 plus 1 over minus 1/2 plus 1. Okay, so negative 1/2 plus 1 is positive 1/2. Okay, and again, divide by 1/2 is the same as multiply by 2. Right, so my antiderivative is -2 u to the 1/2. Again, this is the calculus step. All of this is algebra. All right, and let me put in my x bounds again. So that's minus 2 times 10 minus x to the 1/2. And again, I want the limit as c approaches 10 from the left. And I'm evaluating this from 1 to c. All right, so there's the antiderivative part. Okay, so again, just rewriting it into pieces. I have the limit as c approaches 10 from the left of -2 times 10 minus c to the 1/2. Okay, minus. Okay, and then I have -2 times 10 minus 1 to the 1/2. All right, here's my upper, and here's my lower. Okay, everybody see the fundamental theorem here? Okay, now here's what you want to understand about this, okay? When I say this is approaching 10 from the left, I mean, first I'm saying this is maybe -9. This is like a -9, right? Because that's to the left of 10. 10 minus 9, that's a 1, okay? Suppose this is 0.99, okay? Well, then this becomes just 9.9, right? Then it becomes 1/10. How about if this is 9.99? Then it's 1/100th, okay? So you're imagining this value getting close to 10, but from the left side. Okay, and you can see this gets very, very small. Okay, so this quantity is approaching 0 as I approach 10 from the left. Okay, if you take the square root of 0, you get 0. If you multiply 0 by -2, you get 0. Okay, so that whole expression when you take the limit of it, that approaches 0. All right, so I'll put a 0 over here so you can see what I'm doing. All right, does everybody understand evaluating this expression as C is getting close to 10, but from the left-hand side? Okay, so from the values that are less than 10. Okay, the difference between 9.99999 and 10 is becoming infinitesimally small. It's approaching 0. Okay, so that whole expression is 0. Okay, over here, I have minus, -2, 10 minus 1 is 9. Okay, 9 to the 1/2 means take the square root. Okay, so that's going to give me a 3. So then I have -2 times 3 is 6. And then I have minus a -6. So my total integral value is 6. Okay, once you get to this point, once you've taken the limit, you can just plug this into a calculator. Okay, so let me ask questions on example 4. Questions on example 4? Okay. All righty. Let me do example 5. I'm not seeing questions. Again, if you're not sure how to evaluate this, take your calculator and actually plug in values, okay, that show you're approaching 10 from the left. You start with 9, then you go 9.99, then you go 9.999. See what happens to the expression, okay? You can do it with a calculator if you're not comfortable just looking at it. Okay, let's take a look at this one. Okay, is 1 over x undefined anywhere in the interval 0 to 1? How about this expression? Okay, so I'm asking you for some input. Is this integral undefined anywhere? Yeah, at 0, okay, because then the denominator is 0. Okay, so again, it's my lower bound, so I need to approach that from the left. All right, so I'm going to basically let C approach 0 from the right-hand side. I mean, I'm approaching it from the right-hand side. I'm moving left towards it. Okay, so I'm approaching it from the right-hand side. Okay, from the positive side is usually what that plus sign means. Okay, so take the limit as C approaches 0 from the right. Okay, you might remember that if I integrate 1 over x, I get ln, the absolute value of x. Okay, so that's a simple integral. And again, you have an integral cheat sheet in the Canvas course. So again, have that handy in case you don't have to memorize all this stuff. All right, so now doing the fundamental theorem, I have my upper minus my lower. Okay, so I have at my upper bound ln the absolute value of 1 minus the limit as C approaches 0 from the positive side. Okay. So what's happening to ln of c as c gets really, really close to 0? Okay, so that's what that's asking. And it gets close to 0 from the positive side. Okay. And basically, you can try that on a calculator. All right, let me share my TI with you so you can see what I'm doing. Okay, turn it on. Okay, and I can put ln of x in my function thing here. So I have ln and absolute value of x. Okay, so I can say abs x, just so you're sure I'm not doing anything strange. And then I want to make sure that my table is set up for me to plug in x values. Okay, so I'm going to set this to independent ask and then go to the table. All right, so now I'm letting x get really close to 0 from the positive side. Let's let it be 1. Okay, x is 0. How about 0.1? How about 0.01? How about 0.0001? 0.12341. 0.12345. Okay, what's happening to the y values? What's happening to the y values as x gets close to 0? Okay, let's go into exponential notation. So maybe you can see it even sooner. How about 1 e? Okay, and again, I'm going to give it a large negative exponent. How about negative 10? We can see what's happening here. Okay, anybody, any ideas what's going on? How about if I make that an even larger, more negative exponent? What's happening to the y values? Can everybody see the calculator? Yeah. Well, the y values are getting not smaller. I guess smaller is a good word, more negative, but are approaching negative infinity. Right? They're not approaching 0. They're going the other way. Negative 2.3, negative 4.6, negative 11, negative 13, negative 228. Okay, they're approaching negative infinity. Yeah? Everybody all right with that? Negative logs give you fractions. Okay, so basically that's what you're seeing here. Here's the fraction, here are the negative logs. Okay, so this part is approaching negative infinity. Okay, so it doesn't matter that ln of 1 is something I can evaluate. Okay, that's 0. Okay, this part blows up. Okay, so the integral diverges. The integral diverges. So in other words, that's your way of saying no value I couldn't get a numerical value for this. Okay? The integral diverges. Okay, does this make sense? All right, and if you're trying to understand what the picture looks like, if you look at this in Desmos, you'll see as you get closer and closer to zero, the graph of ln takes off towards negative infinity. Okay, and so the area between the curve and the x-axis gets infinitely large, but it's negative. Okay, so you get an infinitely large negative area. Okay, is that sensible? Everybody okay with that? Let me see if I can quickly show you here. So let me get rid of the calculator. All right, and I will put in 1 over x. Ln x, right, is what I want. Ln absolute value of x. Okay, so I have ln absolute value of x is y, f of x. What happened to my other absolute value bar? All right. Not graphing well. Okay, so this would be trying to get to 0. Okay, and again, I'm not getting a good graph. I'm not sure why. Oh, parentheses, thank you. There you go. All right, so this had an upper bound of 1. And again, let me change this. So there are steps of 1, and I'll make this 10. Okay, so I have sensible bounds now. All right, this is the area that I'm looking at, okay? But again, you can see the area is not going to work, okay? It's approaching a large negative number. And again, my things are not finely controlled enough, but I just want to show you what the area is. This is the graph heading down to negative infinity. And as I move that point closer and closer to 0, maybe I can do it in hundredths, okay? You'll be able to see that I can't really get closer, okay, with the graph, okay? But on the area here heads on down to negative infinity, all right? That's why the integral is divergent, okay? Please feel free to use a combination of things to understand these. Use graphs, use tables of values, and again, just the algebra in the formula, okay? So use all 3. And equations to make sense of this. Okay, use everything to make sense of the limits. Okay, so there's a divergent one. Okay, the last thing I want to show you with improper integrals are like tests that will help you decide whether a given integral should converge or not. Okay. Sometimes, again, the only thing that matters is, can I get a finite number out of this? Okay. And you can decide, okay, whether or not something's convergent, even if you don't want to determine the exact value. Like, for example, say you're the company that's being fined by the EPA for dumping things into a river, right? And you know the rate at which you're dumping. You can model it by a function. It's a rate function. And you know you're tailing off with the dumping, right? So in the indefinite future, okay, because again, maybe you're saying, I can't do my business unless I have some place to dump waste. So I'll pay you a fine based on what I dump. Okay. So you want to know, can I actually come up with a number for how much I'm dumping? So all you want to know is, does it converge or not? Okay. Even though you might not care about the exact value. So again, what you can do is you can compare it to known integrals that you know converge or diverge, okay? And the second test, called the p-test, will help you decide if you've got an integral of the form 1 over x to the p, does this diverge based on the value of the exponent? Okay, so let's take a look at these two tests together. So what this does is gives you a library of divergent and convergent integrals to compare yours to. Okay, so that's what it's doing, right? So let's look at the p-test first, okay, because it's going to give us some standards of comparison, okay? If I have an integral with an infinite upper bound, and I have 1 over x to the p, it's going to converge as long as p is greater than 1, okay? So p is greater than 1. So if this is squared, cubed, right? Absolutely. If p is less than or equal to 1, it's going to diverge. And we just saw it when it was equal to 1, we had 1 over x, and we wound up with ln, and that diverged. Okay? So this is kind of a general rule of thumb. Right? For convergence, divergence. Okay? So let's take a look if these are convergent or divergent based on the p-test. Remember, the p-test is just looking at the exponent on p in the denominator, as long as my upper bound is the infinite one. Okay, so here I can rewrite this like this one. Not p, x to the p, where p is, sorry, 1/2. Okay, so what do you think about that one? Okay, is example 6 convergent or divergent based on the p-test? Okay, here's the p-test up here. What do you think? Yeah. Okay, here p is 1/2, which is less than 1. So this diverges. Don't need to do any integration. Okay, how about this one? This is the one we just did. Okay, so here p equals 1, which is less than or equal to 1. So this also diverges. Okay, again, I don't need to do any calculus. I'm just looking at that exponent. And we did this one as well. Okay, here p equals 2, which is greater than 1. So this converges. All right, so this would actually be worth my trouble to do the integration, because I'll actually get a value out of this one. Okay, don't waste your time, don't waste your time. Yeah, this one might be worth doing. Okay, see how the p-test works. See how the p-test works? Okay. Last thing I'm going to show you is a comparison test for integrals of positive functions. Okay, so if your new integral is smaller than the one you know converges, the new integral converges. Okay, so think of this as like a restraint. If you've got something smaller, then an integral you know comes to a value, well, then the smaller one should come to a value as well. Okay, if your new integral is larger than one that diverges, then the new integral diverges. You can think of your comparison integral as going off to infinity. If your integral is bigger than that, well, it's headed to infinity as well. Okay, see how that works? And again, if it's larger than a convergent or smaller than a divergent, you can draw no conclusions. Okay, so here's where the test fails. Okay, I'll just show you one example of this since we're getting close to the end of the period. Okay, so let me look at this one. Okay, so what integral could I compare this to? Okay, what's a good comparison integral? Okay, well, this looks like the integral from 1 to infinity of, and again, we're losing a dx here. Okay, basically 1 over x squared dx, right? Because the power of x is the same. Okay, I know that this converges, right? Because by the p-test, okay, since p is greater than 1, I know that this converges. So what I have to show is this smaller than that? Okay, I have to show you it's smaller than that. Okay, so let's take a look. Okay, basically I can factor out my 3. And then I have 1 over x squared plus 5 dx. Okay, I know this converges, so I know that this also converges. Right? Because again, if this gives me a finite number, this is just 3 times whatever that number is. Okay, and now I can say this is less than that. Okay, I can say it's smaller. Why is the integral on the left smaller? Why is it smaller? How can I put this in here? Can anybody see what makes this function smaller than that one? Anybody at all? Take a look at the denominators. Okay. Okay, look at the function denominators. Is this denominator bigger than that one? Yeah, the denominator on the left is bigger than the denominator on the right. What did we just say about big denominators? Okay, if this denominator is bigger than that, this function is smaller than the one on the right. They don't necessarily diverge, no. Okay, this is smaller than a convergent function, than a known convergent function. Right? So the function on the left is smaller than a known convergent function, so it's also convergent. Okay? Again, you have to prove it's smaller than a known convergent function or larger than a known divergent function. Okay? Does that make sense? So does the reasoning make sense? Okay, I'm just asking you about example 9. Does the reasoning make sense? Okay, we're comparing it to a known convergent function. We're showing because its denominator is bigger, it's smaller than that known convergent function, so it must also converge. Yes? I'm getting crickets. Okay, ask a question if it's not clear. Ask a question if it's not clear. I'm smaller than a known convergent function, so I must also converge. How do I know I'm smaller? My denominator's bigger. Bigger denominators give me smaller fractions. Yes? Okay, example 10 is going to compare this to a known divergent function, and it's going to show it's bigger than it, so it must also diverge. Okay, I will show you the work for this one. Okay, but we're kind of running out of time at this point. Okay, so let me ask questions on anything to do with improper integrals. Questions on anything? Alrighty. Coming back to the meeting. All right, questions on anything at all? Questions on anything at all?